Hello students, in this video lecture series, we'll discuss the magnetic field due to current carrying solenoid. Student, what is solenoid? A coil of many circular turns of insulated copper wire wrapped closely in the shape of a cylinder is called a solenoid. Say suppose you have a straight copper wire, insulated copper wire, if you wind it in the shape of a loops, closely wrapped loops, you get an arrangement which is circular, cylindrical. So the arrangement is called a solenoid. So that's what we mean by this line. A coil of many circular turns of insulated copper wire wrapped closely. Wrapped closely means these are the turns where there is negligible gap, negligible space. In the shape of a cylinder is called a solenoid. So that's what the solenoid. It's a coil. Now if we allow the current to pass through this coil, what happens? This also becomes the source of the magnetic field. So now let's discuss what is the nature of the magnetic field around this solenoid. How do we determine the direction of the magnetic poles, the north pole and the south pole? And what's the nature of the magnetic field around current carrying solenoid? Let's discuss. Student, magnetic field due to solenoid. The first point is the magnetic field lines around the current carrying solenoid is same as that of a bar magnet. We have discussed about the magnetic field lines of the bar magnet. So same as a bar magnet means the magnetic field lines, if you remember, we've discussed, suppose we have a north pole and south pole. This is the bar magnet. The magnetic field lines starts from the north pole and terminates at the south pole, outside the magnet. That's what we studied. It's like this. Same here. So one end of this solenoid will behave like a north pole and another end of the solenoid will be behaving like a south pole. So student, this end of the solenoid will be a north pole and this end of the south pole, this end of the solenoid will be south pole. If you allow the current to pass through this end, say suppose the two ends of the solenoid, these are the two ends of the solenoid. If I connect this two ends to the battery's terminals, positive and negative terminal, if I plug the key, the current starts flowing. If I allow the current to flow this way, so this end of the solenoid will be north pole and this end of the south pole. This will be behaving like a south pole. If I reverse the direction, if I reverse the polarity of the battery terminals, say suppose if I make this positive, if I allow the current to flow this way, then this terminal, this end of the solenoid will be behaving like a north pole and this end of the solenoid will be behaving like south pole. So if this is the north pole, so field lines will start from the north pole and terminates at the south pole. So inside the solenoid, the field lines will be starting from the south to the north. So student, outside the solenoid, you can see outside the solenoid, the magnetic field lines are not same everywhere, not distributed uniformly. So magnetic field outside the solenoid will be non-uniform in nature. But inside the solenoid, the magnetic field will be uniform in nature. So you may be asked, name one source of a uniform magnetic field. So we can say it's inside the solenoid, the magnetic field nature will be uniform. Students, this is the diagram to represent the uniform magnetic field where we draw straight lines of equal length and equidistant, equispaced. So you can see these two lines are of equal length and they are equally spaced. So that indicates the uniform magnetic field. You can see this end is the south pole and this end is the north pole. This is inside the solenoid. You can compare here. This is the south pole and this is the north pole. So south pole and north pole. So this is what the uniform magnetic field. Now student, magnetic field around the current carrying solenoid depends upon what? So three important factors. It's a current. So magnetic field is directly proportional to current. If you allow the more current to pass through the solenoid, the magnetic field around this solenoid will be strong. If you allow the less current to pass through the solenoid, the magnetic field will also be less. Number of turns. Suppose you have 1, 2, 3, 4 turns here. If you increase the number of turns, current carrying loops, the magnetic field will also be strong. And the most important, the last one, the core inside the solenoid. If you want to increase the strength of the magnetic field, you insert the magnetic materials inside this tunnel-like structure of the solenoid. So that intensifies the magnetic field strength. So that's what we call a core. Now, how do you determine the polarity? As I mentioned just a while ago, this end of the solenoid will be north pole and this end south pole. How do you determine this? Experimentally, we determined taking a bar magnet. Let's say, suppose I have a bar magnet. I don't know which end of this solenoid will be behaving like a north pole and which end will be behaving like a south pole. We don't know because it's invisible. So what do? We take a bar magnet. Let's say, suppose this is the north pole and south pole. If I take this bar magnet and if I bring this bar magnet close to this solenoid, two possibilities will be there. Either this bar magnet will be attracted or it will be repelled. So now I know this end is the north pole. If I bring this close to the solenoid, if this is attracted inside the solenoid, so of course this will be south pole. This end of the solenoid will be south pole. But suppose if I bring this bar magnet and if I find this bar magnet is repelled, that means this end of the solenoid will be the north pole. That's how we determine practically, experimentally, the polarity of the solenoids. Student, one more point we will discuss. That's what? Force on a current carrying conductor. So we have completed the magnetic field produced by the current carrying straight conductors, current carrying circular loops and current carrying solenoids. Now let's discuss one very important point, that's force on a current carrying conductor. Student, suppose you have a current carrying conductor. If you place that current carrying conductor in a magnetic field, experimentally it has been known that the current carrying conductor experiences magnetic force. So when you place a current carrying conductor in a magnetic field, it experiences force. That's one important observation. So when a current carrying conductor is placed in a magnetic field, it experiences a magnetic force. So if that magnetic force, if the current carrying conductor experiences a magnetic force, so which direction the current carrying conductor will be experiencing the force? How to know this? So direction of force changes when reversing the direction. Student, one more important observation. We have an arrangement made here. Suppose this is a U-shaped magnet. U-shaped magnet. So inside this, between these two poles, you have suppose north pole here and south pole here. This the two arms of this U-shaped magnet. So here is one arm which is north pole. This is another arm which is south pole. So between these two poles, there is a magnetic field which is directed from the north pole towards the south pole. Student, remember, the magnetic field is always directed from the north pole towards the south pole. So now here we have a conductor. This is the conductor which carries current in this direction. So this arrow indicates F. It means this conductor which carries the current in this direction, which is placed inside the magnetic field of this U-shaped magnet, experiences force inward. That means this conductor which is carrying current will be displaced inside this U-shaped magnet. Now if I reverse the direction of the current without reversing the direction of the magnetic field, in this case also you can see the direction of the magnetic field is upward from north to south, but I have reversed the direction of the conductor current. So if I reverse the direction of the current, experimentally it is determined this conductor experiences force outward. So this conductor will be displaced outward. Now how do we know? So this current carrying conductor experiences force which directions? So the direction of this force which the current carrying conductor experiences on placing inside a magnetic field is determined by a rule called Fleming's not right, it's a left-hand rule. Fleming's left-hand rule. Now student, what does this rule says? This rule says to determine the direction of the magnetic force, you have to stretch the first three fingers of your left hand mutually perpendicular. Say this is left hand, Fleming's left hand. Now if we stretch the first three fingers of our left hand mutually perpendicular, you can see all these three fingers, they are mutually perpendicular stretched. Now you have to adjust these three fingers in such a way that this finger indicates the field, magnetic field. This finger, the central finger, indicates the current. And this finger, thumb finger, represents the thrust. So student, you can remember like this. This T T stands for thumb, and T also stands for the thrust. Thrust is a motion. The thrust is a force. So force causes motion. So this thumb will give you the direction of the motion or the force which the conductor carrying current will be experiencing. Now this is what forefinger, F for 4 and F for field. So this will be pointing towards the field. And this is what central finger, you can see. This is the center finger. So this central finger will be pointing towards the current. C for center and C for current. That's how you can remember this. So stretch the first 3 fingers of your left hand mutually perpendicular to each other. In such a way, you adjust these 2 fingers first. This finger should be directed towards the field and this finger should be directed towards the current. So when you adjust these 2 fingers, this thumb will be pointing towards one direction. So that direction will give you the direction of the force. Let's just understand. Suppose you have this magnet, U-shaped magnet. So student, let's say suppose this is the north pole and this is the south pole. I have a conductor which is placed inside this magnetic field. This is the north pole, imagine. This is the north pole and this is the south pole. You have a region here between these 2 poles which is magnetic field. You have placed a current carrying conductor perpendicular to the screen of your cell phone. The current's direction is towards you, coming out of the screen. So now this is the current carrying conductor which carries current upward outside the screen, perpendicular to the screen outward. This conductor will experience a force because this conductor is placed inside a magnetic field. Now how will you determine the direction of the magnetic force which this conductor will be experiencing using Fleming's left hand rule? Now student, I hope you remember what is the direction of the magnetic field. Imagine the direction of the magnetic field is from thumb to this index finger, forefinger. It's upward. And the current's direction is perpendicular to the screen towards you. Now let's use the Fleming's left hand rule to determine which direction the conductor will be experiencing force. Now as I mentioned, you have to adjust the first 2 fingers first. So you remember which direction the magnetic field was there. Magnetic field was towards this side. You remember this arrangement? You have to remember this arrangement. So here is the magnetic field directed from north pole to the south pole. So this is the direction of the magnetic field. And the current was directed perpendicular to the screen upward. So now use the Fleming's left hand rule. So first you have to adjust these 2 fingers. This finger indicates magnetic field. What was the direction of the magnetic field? It was this side. This is the direction of the magnetic field. This is the Fleming's left hand rule, student. Remember, not the right hand. Fleming's left hand rule. So this is the magnetic field's direction. I have adjusted this finger towards the direction of the magnetic field. Now I have to adjust this finger, the central finger, in the direction of the current. What was the direction of the current? It was perpendicular to the screen outward towards you. So adjust it. So this is the direction of the magnetic field which is pointing towards you. And see, when you have adjusted these 2 fingers, this finger, index finger and the central finger, where is your thumb pointing? The thumb is pointing towards your left side. This is the direction of the thumb. It means the conductor which were placed here like this current carrying conductor will experience the force inside. So it will be displaced inside. So that's how we can determine the direction of the magnetic field. If I reverse the direction of the current this way, suppose if the current is directed downward towards the table perpendicular away from you. So in that case, also the magnetic field direction is same, upward. So use the right hand thumb, Fleming's left hand rule. So in this case, magnetic field remains same, but this time the current direction is away from you. So the central finger is pointing downward. So in that case, the thumb is pointing towards your right side. That means in this arrangement, the conductor will be experiencing the force towards your right side. So it will be displaced outside the magnetic field. So that's how we determine the magnetic field. The force experienced by current carrying conductor placed in a magnetic field. Student, I hope you understood how to determine the magnetic force experienced by a current carrying conductor placed in a magnetic field. So with that, we end today's lecture. So thank you.